This is what Adel Bashir taught this in the spring. This is the book he used. It's his book. He lent me it. So I assume this is the book he meant for the course. But that book, just looking at it, is better. It has more applications towards signals and systems and not just cards and beer and wine and stuff like that. I think for problem 150, I'm gonna start with conditional probability, but for 150 they have, I think, 4 categories. I want to do this problem before I keep going. And you have access to this. You got it. Go ahead, read it.
The population of a particular country consists of 3 ethnic groups. Each individual belongs to one of the 4 major blood groups.
All right, and this is kind of interesting because this one, at least it gives you a good visual of what's going on here. So this is going to be, I think, call this ethnic group 1, ethnic group 2, ethnic group 3. And this is, I think he has A.
It goes O, A, B, B.
O first. Okay. I just want to put this up here. We got a minute or two. It's 150. So these are the blood types, and it's O, A, A, B, or is it
B and then B.
A, B. All right, so this is the blood types. And then it gives the distribution, the probability, or the percentage of the people that have these different blood types. What's in here?
0.082.
Oh, 082? 0.08.
Point, yeah.
Go ahead. Down here?
0.135. 0.215. 0.106. 0.141. 0.200. 0.008. 0.018. 0.065. 0.004. 0.006. 0.02.
All right, so that's the percentage or the fractional amount that each have these different types of blood type. These are the ethnic groups. There's 3 different ethnic groups. Now this is like a standard thing just to give you a kind of a visual. So he's going to ask for probability of all these different things, conditional probability. And I think I'm about on time, right? I can start? Just wanted to get that up there before start. So for conditional probability, the first thing I always do is draw a Venn diagram to give you a visual. And if you have, doesn't matter how many, but we'll start with just 2. If you have A and B as possible groups there. So if you have the probability, you want the probability of A given that B occurred. That's all that this means. B has happened. What is the probability that A happens, given that B occurs? So for this one, if you look at this is really going to be something where this area becomes critical. So it's really the probability of A intersect B. Y'all follow me? That's this stuff I shaded out over the probability that all this happened right here. This is the rest of B over the probability of B. Before I start, how many looked at this problem and tried? Everybody follow me on this? The rational thought behind it. So I want to go through this one. The reason I like this one more so than others is because there's a limited amount of stuff you can actually see. We can get a visual on how that relates to that. Y'all follow me on this, class? First, he gives us stuff. He wants to know what's the probability of being, I think, A-type blood and then B-type blood. Is that right? And then I think it's ethnic group 3. So he's going to say P of A is just going to be A-type blood. And then P of B is going to be B-type blood. Again, this is problem 150. And then probability, he calls C, that they're members of ethnic group 3, right? Is that right? Okay, so now we'll call that C. So first he wants, I think, the probability of having a blood type A. Is that right? First one? So he wants the probability of A. No conditions on this. This one's straightforward. Here's A. Just add them all up. Y'all follow me? By the way, if you add them all up, it comes to 1. It has to, because these are fractional amounts. Y'all follow me, class? So for this one, it's 0. By the way, when I was doing this last night, I got rid of that decimal point. I just calculated the numbers, because the ratios will be the same if you multiply everything up there by 10 or by 1,000, and you just take ratios and numbers, you get the same thing. But for this one, probability of A is going to be, we got 106, 141, and 200, so it's 0.106, right? Plus 0.141 plus 0.200, and that's going to be what? That's 0.2, and that's going to be 0.341 plus 106. That's is that 44? What is that? 7, yeah. 0.447 is the probability it's A, and I think that's right, if you look. I gave you the solutions, right? Right? Next one is probability B, is that right?
Right. No, probability C.
Or probability C?
Yes.
All right, well, C is this ethnic group, and here we don't do column, we're going over this way. So we're adding a row, so we're going to add all these up, right? So I got 215 and 200 is 415, and 2 is 417 and 65, right? Or 0.065. What does that come to? 0. What's that? 0.4. Is that 0.487? Is that right? Huh?
Should be 0.5.
Point what?
5.
Oh, I'm sorry, 0.57, 87?
No, it's just 5.
0.5, all right, well, I messed up. Are those numbers right? 0.5?
Yes, sir.
Okay, I'll trust you. I think you're right. All right, and then now this is just basic. You're just looking and adding. That's all you're doing. The next part is conditional, right? So what do they ask for?
A intersects C.
Type A blood in group 3.
All right, so then they ask for this. The probability of a person having type A blood and being from group C. Is that it?
Yes.
All right, this is one of those things. Here's the probability of type A blood, right here. And here's group C right here. So when you think the way I'm trying to present this, when you think of this, if we have A and C, right? What we're really trying to do is this, and you'll see it in a second. It's not very hard. This is really going to be the probability of A intersects C over the probability of C, and it's really areas here, or fractional amounts. Do y'all follow me in this class? So if you take a look at that, here, the probability of C is just adding all these up, right? Y'all follow me in this class? So that is 0.5, which is nice, 0.5. By the way, some of these answers are wrong as far as the addition. They have the right idea, they just add them up.
This one's all correct.
Okay, but I don't know which one's messed up, but I think one or two of them have wrong answers when they have the right numbers, the wrong answers. All right, and then, so the intersect area is this right here, and that is equivalent to what? Well, that intersect area is right here. Do you all see this in class? That's where they intersect, so it's 0.2, right? 0.2, and that means this is 0.4 for probability of A given C. And is that right in the book that you have? Class?
Yes, sir.
Y'all follow me on how I did? How many see this? How many tried this again? All right. I hope I don't know if I'm trying to make this clear, going through the simplest possible problems then you'll see how this, especially when we get into continuous random variables, how this directly applies to it. And then what's the next part he asked for?
He wants the probability of C given A.
All right, probability of C given A. All right, so I can just do it this way. Now it's the probability of C given A, and I'll put it right here. You can see on top it's the same thing, right? So first, the probability of A is just what? Adding, or probability of C down here given A. So we're going to add up that column. That's A, right? Y'all follow me in that? And what is that probability of A is 0.447. And then the intersect area of CA is right there. Isn't that right, class? So that's just going to be 0.2. What's this come down to?
That's what I got when I put my calculator.
0.447? Okay, I'll go with you. Doesn't look like 4.5, but I'll go with 0.447. If,
That is
huh? If it was point, okay, I'm gonna just leave it like that. If it was 0.4, it'd be 0.5 on top. 0.4, okay, I'll give it to you. Odd, isn't it?
It is 0.447. There's more numbers behind it, but
That's all right, we'll just leave it. All right, so that's probability of C given A. But you kind of see this aerial business. Here's what I always tell people. Whenever they give you something happens, if C happens or A, this happens, use that area. Then the probability, given this happens, that's the area, and you want the probability that's a subset of that happen, which is this sliver. It's just the ratio of this area in the sliver to this area in C. Do y'all follow me? And I try to get people to think that way because it'll help you a lot, I think. I know the areas are just, the area is proportional to the percentage that that event would occur. That's what it really amounts to. But the ratios always are a ratio of, you consider the areas of these events in a Venn diagram. Make sense, everybody? All right, what's the next part?
If the selected individual does not have type B blood, what is the probability that he or she is from ethnic group 1?
All right, so what he's saying is the probability that does not have type B, right? So I'm gonna write it this way, and I think he does too, or B dash, you know, it's not that, right? And it's from group A, right?
What is the probability that he or she is from ethnic group 1?
Oh, ethnic group 1. All right, so now I think he creates another column. So we've got ethnic group 3, here's ethnic group 1, so we'll call probability being from D equal to ethnic group 1 that's here. So now, first of all, I've got to add all those up. Do y'all agree with that? So that means, what is this going to be? Let's see, 4 and 8 is 12, 94 and 106. 0.2, is that right? 0.2. So this is 0.200. So now, draw the Venn on this one. Remember, this is S. It's all possible outcomes of the events. So now we want the probability of B prime, or it's not being in B, not being in this group right here, given, so it's not B and it's in this group D, right? I think he does it this way. All right, now I'm going to say one thing here. If you think about this, the probability of D given B plus the probability of D given B prime, I want you to think about that for a second. All right, first, when you talk about B or B prime, so here's B. B prime is everything else. Do y'all follow me? That's all B prime. Probability it's not here, but it's in this group. Now, here's the, I think I can draw this. So if this is D, and this is B, right here, then if I take a look at B prime, just for a second with this marker, B prime is everything outside of B, including D right here. Y'all follow me on that? Follow me? Now, if you look at this, B prime plus B, the probability of B prime plus the probability of B has to be 1. Do you agree with that, everyone? Now, let's see if this works. So if I come here and I take a look at this, right here, if I found the probability of D, well, let me do it this way. I believe I can make this case. This will equal 1. And here's what I'm saying. Just listen to me. They're saying this event occurred and this event occurred. That's the whole place. Do y'all follow me, class? Everything, in other words, actually, I'm saying this and I'm catching myself right here, but if I take a look at this, all this area outside here that I got in, isn't that really 1 minus the probability of B? So I'm going to say this area is 1 minus the probability of B. I think I can do it that way better. This will make more sense to you. Now, if you look at this, the probability of D given that, right? So this event basically occurred that I have here, right there. Agreed? Now what's the I mean, it's all outside there. This occurred, but what's the area in D? So what would it be? If we take a look at this, probability of D given B prime. So B prime, the area down here, is going to be 1 minus the probability of B. And then the intersecting area is this that I'm trying to show you. Agreed? So what would that be? Well, that's the probability of D, right? Minus what? Minus all this right here. Agreed? Minus the probability of, and it would be D intersect B. There's probably an easier way to do this. I think you can do it with just, you can use what I had up here, probability of D over B prime plus probability of D over B is equal to 1. You can do it that way, but I wanted to show you with area. Do you all see what I'm doing here? All right, so what is this going to be? Well, probability of D given B prime. Here, 1 minus the probability of B. What's the probability of, it's, sorry, of blood B. We got to do that. What is that going to be? It's 0.026 plus 0.065, right? Is that 0.091? 0.091, correct? So that's down here. Now upstairs we have probability of D, and that's all that. We put it down as 0.2, correct? That's this right here. It's just the probability of all this. Agreed, class? And then I have to subtract from it the probability of D intersect B. All right, now just look here. Here's D, and here's B. Can you all see it's 0.08? All right, so it's that minus 0.08. And what is that answer? Go ahead and do it, just see if it...
Is it 0.008?
Oh yeah, sorry, my bad, my bad. When I did this at home, I got rid of that point crap. I just multiplied top and bottom. Yes, sir. I mean, just do, if I miss a decimal point, forgive me. Yeah.
You did the math all right with the numbers, but you're already supposed to put B not. Oh wait, never mind, never mind.
The pink, I mean that purplish pink thing, that's the not B. That's what I'm trying to show you.
Is the bottom supposed to be 1 minus what you got there? Because that's the probability of B, the 0.091.
Oh, yeah, it's supposed to be 1 minus, I'm sorry about that. Yeah, 1 minus that, I'm sorry, 0.091, right? I'm sorry, 91. Can you tell me what that is? I'm sorry about that.
You have 0.211 if you plug that in.
Sounds right, I think it is, but I don't. 0.211? Is that
Yes.
right? It is? Okay. But I'm going to tell you about this. There's other things you can, I'm just trying to do this in a way that's visually useful to do. If you take a look at this, everything that's not B is outside of there. Well, if it's not B, the probability of B plus not B is 1, right? So that's why I got this down here. Then when I take a look at this, I need all this area in D discounting that. So I have to find the intersection of B and D and subtract that from probability of D. That's the way I did this. I'm sorry if I put decimal point. But you all follow me on this, class? All right, now this problem really, in my opinion, it's trying to give you something where it's a fairly small amount of information and you can get the visuals with the Venn easy with this, all right? Because these things get really confusing when you got a whole bunch of numbers and you haven't got a good feel for this and all sorts of things, especially when you get 3 or 4 different things that have overlap. Then you have to, subtract off a whole bunch of stuff. Okay, that's 50, right? Problem 50? All right, we'll do 51 too. I thought it was a good problem because it's fairly easy to track. It's not super complicated. Some of the ones in his book, the latter ones, get really complicated. All right, 0.51. Can you go ahead and give me that one anyway? Yeah.
So an individual from USA that's an adult male is selected, and let A be the event that the person is over 6 feet tall.
Oh, this is a weird one. All right. So event A, and I'm not even going to put a probability.
The male is over 6 feet tall.
It's male greater than 6 feet. Go ahead.
And then B is the person is a NBA player.
So NBA player. All right, so the person's an NBA player. Okay, now he wants probability A given B, probability of B given A. There's just one thing you have to assume. There's a lot of people over 6 foot tall, but there's not a lot of people in the NBA, even though they're tall. So if you think about this, we'll call this P of A, and we'll call this P of B. He doesn't even give an answer, a direct answer for this. He just kind of mumbles about it. All right, so let's see. Male over 6 feet tall. A. NBA player. Well, not many NBA players. All right. I'm trying to draw this in a way that's meaningful. Something like that. Agreed?
I think it's more likely for an NBA player to be over 6 feet.
All right. It doesn't matter. You're probably right, but I don't know that for a fact. I'll give you that. How about we do this? We'll do, just agree? B, all right? So, not drawing a scale by any means, but it'll give you, he's just trying to give you an insight. So, what is the probability that a random male selected, and he's just asking for this, P of A given B, and P of B given A. He wants to know which one's bigger. So here, if he's an NBA player over 6 foot tall, I'm going to say it's greater than a half. I don't know if that's fair or not. Because
Not 6 feet.
What?
There's not very many NBA players that are under 6 feet.
No, and to be honest with you, he did this just as giving you a mental tool to sort of stretch your thought process, make you think about something at least you should know something about. So I'm going to say that the probability he's male is all this, right?
It's the whole circle.
Huh?
Isn't it the whole circle? Because A is just that they're over 6 feet tall.
Oh yeah, I'm sorry. He wants the probability that B occurs. I'm sorry about this. Let me do it. I'm sorry. So probability of B occurs. So here's the area in B right here, okay? And if B occurs, the probability it's here. Y'all follow me? But B occurs, so it's really all this area divided into this area. Do y'all agree it's greater than a half probably? With me on that? If an NBA player is selected, there's better than a half chance that he is over 6 foot tall. And I'm just doing this randomly. Now, the second part is, what if you select somebody just randomly? What's the probability he's an NBA player? I'm going to say it's a lot less than a half. I mean, it's just a vision. Do y'all agree with that? That's all he's saying. So this is going to be probably a lot less than a half. But again, it's just one of these things to give you an idea of if somebody is selected as NBA, trying to give you a mental picture of these ratio businesses. That's what I call them. They're really area ratios. Do y'all see this, class? We could give exact numbers, but I think it doesn't really need to be done. All right, the next, y'all with me? Next problem. Let me erase this. And the reason I do these problems, I do a lot of these problems, because oftentimes there's subtleties that will confuse you. And if I put it up there and we discuss it, hopefully they'll come out. Last time I taught this class, I didn't do a lot with Venn diagrams, and I regretted that. I think this is very useful. Y'all, is everybody following me the way I'm teaching this right here? Okay, next 53. I forgot what it was.
Was it 52?
Or 52, pardon me. Wait, what is 52?
The credit card scenario?
No, it was 53. The reason to consider the system.
What's that?
It's the system defect one, right?
No, is it 52?
I thought we had 52. You just have both of them, I think.
All right, what is 52?
It wants you to go back to the credit card scenario exercise.
All right, we'll do 52. All right, we might as well do them in sequence because all these are good problems. I mean, I don't remember the whole thing on this. Go ahead.
So A is Visa, B is MasterCard.
A is probability of A is a Visa card is selected, right? And probability of B is what?
MasterCard.
MasterCard, go ahead.
And then the probability of A is 0.5.
Okay, so this is 0.5.
And then 0.4.
0. What?
4.
Okay. I'm going to try to draw a Venn of this because he gives a probability of, he gives something else.
And then A intersect B is 0.25.
Oh, probability they own both cards? Is that right?
Yep, 0.25.
0.25. Let me try to draw this, but I think you all can already get a visual on this. So first, here's the S that indicates the total number of possible outcomes. And the probability of that has to be 1. I really talk about the probability of S being 1 in there. It has to be one of these outcomes, okay? Now, then he says that A, which is the probability of Visa card, is 1/2. And he talks about B, the probability of a MasterCard is 0.4. But this intersected area is 0.25. Follow me on this, everyone? This is not a hard one, but it's good to see this. So go ahead now, ask.
Probability of B given A.
Okay. It's like the basketball thing we just did. Probability of B given A occurs. All right. Here's A, right? And I'll just write it. So this is what? Technically, this is probability of A intersect B over probability of A, or the ratio of the areas, imagine it that way, fractional. Follow me on this? Okay. So what do we see here? Probability of A is 0.5. And then, what about this intercept? They give it as 0.25. We don't have to even go through any trouble to calculate. So this is 1/2 or 0.5, 50% chance. Agree, class?
Yes.
Now, what's the next one?
Probability of B not given A.
Of what?
B not given
All right, given A. All right. Try to do a visual on this. So again, A occurs, which is this thing. Let me just show you A occurs. That's A occurs is this. So this occurs, and then they ask for B naught. Now, just try to follow me on this. What is B naught? It's anything that's not B. You see, anything that's not B, given A occurs, is this area right here. I think of it as an area. I know that's not exactly right. Do y'all follow me on that? This would be the B naught. So it's really a ratio of areas. So it says the probability of A occurring is all this. Agreed, class? That is going to be downstairs. So this is probability of A. And this is probability of B naught intersects A on top. Probability of A is 0.5. And then probability of this area, now here's the way I'm doing this. If this in here, all the stuff that I'm showing you here is equal to 0.25, it means this has to be 0.25 as well because there's exactly 0.5 total. Y'all follow me? All right, so I'm just gonna say this on top is 0.25. I believe it's right?
That's correct.
All right, so this is gonna be 1/2 as well, or 0.5, correct, class? Now the next part, I think you messes this one up, but I don't remember exactly. You get the wrong answer. The next part is what?
A given B. Probability A given B.
Okay, maybe he doesn't. Probability of A given B. Let me try to redo this just so you can see it. I think it's, yeah. This right here, 0.25. So here, that's the probability of A intersect B over probability of B. And I always say it's the ratio of areas. I hope you don't mind me using that kind of terminology because it really, to me, it is. When I look at this diagram is proportional. So probability of B is 0.4. And now, the intersecting area that they give you is 0.25. Agreed, class? So what is that? Is this the one he has wrong in the book, in the solutions? Or not? He's got a couple of them.
Oh yeah, he does. He says 0.6125.
Y'all hear that? So the solution is wrong. If you go nuts, he's made a mistake. This is right. He has that, but this is wrong. He puts a one, I don't know why. But it's probably a grad student that did these. Okay. And they got a lot on their mind. So that's that. Then he asks, I think one more thing at least. Right.
Probability of A not given B.
Okay, this is interesting. So now, probability of A naught given B. In his book, I use this, he uses this. They're the same thing to me. A lot of books have that bar over it. It means just everything but. That's all it means. Okay, so this is what? Probability of A naught intersect B over probability of B. For probability of B, that's 0.4. Agreed, everyone? Now, what is this? A intersect A prime, or A naught intersect B. All right, here I'm gonna just do one thing. All right, so B occurred. What is A naught? Okay, here's A. A naught is what? It's everything but A, agreed? That's what I'm trying to show you. So when we talk about the probability of intersect of A naught and B, we're really talking about this area. I hope you can see this. Okay, right here. Agreed, class? So the whole area is 0.4, but we have to subtract 0.25 from it. So it'd be 0.4 minus 0.25, right? And that's what, 0.15? Pardon me? Over 0.4? What's that? Now check, is that the right answer?
No, it is
No, I mean, what is the answer?
It's 0.375, that's the right answer, but in the book it says 0.3.
0.375? Is that the right answer?
Yes.
All right, I worked these out. I actually modified my solutions, but I didn't post them. Just go ahead and do that, all right? Do you all agree with that? This is right, but he has the wrong value here. And does he have one more on that one or not?
Yes, it's probability of A given A,
Probability what?
probability of A given A union B.
Given that A union B occurs? Okay, this is interesting. All right, I'm going to erase this and keep using this pen, okay? It may not be necessary, but I'm going to do it because I think it's useful. So here is my A, 0.5. Here's B, 0.4. This area here is 0.25, correct? All right, now he says the probability of A, given that A or B occurs, but not both. I hope you can all see this. The probability of A is just that area, which is 1/2. Agreed, class? So when I look at this, I have 0.5 on top. Now, what is the union of A and B? Well, it's what? It's this area plus this area subtracting the common part. Really, if you just if you just take the outline of this whole thing, that's the area we're talking about. Can you all see this? All right, what's that going to be? Well, it's really going to be what? 0.5, right? Plus 0.4 minus 0.25, agreed? Or really it's 0.25 plus 0.04, correct, class? So this is going to be 0.25 plus 0.4. And what is that? I think this one's wrong too, but I don't remember. Just do the math, because I think it's wrong. I don't remember. He has the right math here for the equation, gets the wrong answer.
It should be 0.77.
Check it. 0.77?
You got this one correct.
We did. Now, hold on.
It's like the 4th decimal place.
Okay. Everybody agree with it? Okay. 53, right?
You didn't put that, but I did it.
I didn't put that down?
Yeah, it was just 51 and 52 on the.
All right, I'm sorry. I want to do 53 and we may do 54, only because I think this is beneficial to see all this stuff done at one time. I can move on if you feel it's too repetitive, but I honestly think some of this helps. Matter of fact, why don't you guys talk me through this? So this is 1.53. Which one is this? Go ahead.
It wants you to go back to the stuff it gives in Problem 28. So the system can experience 3 different types of defects.
I'll tell you what. This one I think is a little long. Why don't we move on to 54? I think we can go there. I think that's the one. 53. It's same exact stuff we did, but it's a little long. I think. Huh?
It was.
I mean, we can do 53, but 54, I want to do some of these things that are meaningful. Go ahead.
So it's type of coffee selected by someone purchasing a single cup at an airport.
Hold on.
So the table has regular and decaf on the left side.
I'll say, so we got regular and decaf, right?
No, it's
Huh?
both on the same column.
So, okay, we got regular and decaf coffee.
Yeah. And you got small, medium, and large.
Over here?
Yes.
So we got, so this would be small, medium, and large. Now, again, he's doing this just to give you an idea of how to kind of build a Venn diagram. Does he show the Venn diagrams in the book on this or not?
Sure.
If he doesn't, he should, because that's how you can appreciate Venn diagrams, by literally taking this and turning it into a Venn diagram. Anyway, then he gives you values, right?
Yeah, so 14%, 20% down right below that. 20%.
Here?
Yes. 10%. 26%. And then 10%.
Okay.
And then the first question is, what's the probability that the individual purchased a small cup? And then also find the probability that they purchased a decaf.
All right, we'll do first probability best. Just take a look at this. If you didn't do them, just go with me on this. What is that going to be? He wants the probability it's a small coffee. Do all those add up to be 1? Yeah, they do. What's the probability it's a small coffee? It's exactly going to be this, 0.34 or 34%. Now, what else? Probability it's decaf? All right. What's the probability it's decaf? Just look. It's going to be, yes, it's going to be what? This is 0.2, right? A decaf, did you say?
Yeah.
All right, so this is 0.2, this is 0.2, 0.4. Agreed? Everybody? This is a nice quiz problem. Nice, easy quiz problem. Math is simple. Everything's simple.
It is a quick quiz question.
Yeah, it is.
All right, so part B, if we learn that the selected individual purchased a small cup.
Hold it. So now we're going to say the probability, and here he's purchased a small, but go ahead.
So what's the probability that they will choose decaf coffee, and how would you interpret this?
All right, we'll do a Venn on this one. So this is D, and this is S, right? So if we look at this, what we're really talking about, probability that's small, so it's probability selects S, so downstairs P of S, and then on top it's P of the intersect of D with S, right? You don't even need that Venn for this one. There's not enough going on, but it helps at least to draw it and see it. Okay, what's the probability of S? We just did that, 0.34, right? And then what's the probability of a decaf with S? So this is kind of a no-brainer. Probability of decaf is this, right? Agrees, everyone? It's really that easy for this problem. So this is 0.2 on top. What's that value going to be?
0.588.
0. Is that right in the book, by the way? Can somebody do this? I'm beginning to be
That's correct. That is correct.
0.588?
Yes, sir.
Okay, or 58.8%. What's the next part?
If we learn that they selected a decaf, what is the probability that the small size was selected?
All right, now we want the probability of small given a decaf is selected, right?
Yes.
What changes?
P of S goes to P of D.
This stays the same on top. Do you all follow me on that? All right. Downstairs it becomes this, doesn't it, class? He's saying probability, a decaf was selected, what's that? Well, on top it's still 0.2. What's it on the bottom? 0.4. And that's exactly really 50%, 0.5, or 50%. Agreed? What's the next part? This is a trivial.
It just said, how does this compare to the corresponding unconditional probability from the first question?
Well, it's a subset. That's all it is. I don't know what he says in the book, but that's all it is. Agreed? Okay. Now, I gave you the PowerPoints, but I'm going to go ahead and do some things. And in his book, this is in chapter 2. I'm kind of skipping out of this. Most of the stuff that he's going to be talking about is how do you tell two events are disjoint. And if they're disjoint, then the probability of one event given the other occurred is just the probability of the one event. And I'm going to explain this in a second. I have a bunch of little things to talk about. And let me go back. it's really called independence, and I'm gonna go ahead and do this, but I'm going to do a few more problems, and we'll get to continuous random variables and expected value, and the second moment, and then the variance, and a lot of stuff that you see. Have you guys had a statistics course yet or not? Do you have to take one or not? Do you have to take economics?
Engineering.
Do they do that? Engineering econ, do they do that in there? No? It depends on, I guess, on who's teaching and what they care about, but a lot of times they do a lot of statistical stuff in business courses and economics and things like this. And they cover in your course, but.
I think we did like a cost benefit analysis type.
Let me ask you this, do they go through the difference between macro and microeconomics or not?
She mentioned.
They didn't show you how to, I'm asking. I can look this, all right. So now, he makes a big point about this, but it's not that. If we talk about independence, when events are independent, on a Venn diagram, if you have A, whatever that event is in B here, and there's no overlay, there's if it's really if and only if, that A intersect B is 0. If that's the case, then they are independent. All right, and to be frank about it, well, there's things that he says. Most of this is just obvious, but he does it this way. So the probability of A intersect B, well, hold on. Let me tell you where it is in his book, because honestly, the way I tell this, if I take one look at this, if these two don't share any common outcome, they're independent. That's how I do it. I don't need any other information. But in his book, what he does, and I'll try to tell you where this is so you'll appreciate this a little more. This is on page 44, and he does it with an intersection. He says, if events are independent, then the probability of A intersect B is just P of A times P of B. All right, now, I'm trying to show you something on this one, just appreciate it. If you have things that have no intersection, no dependence on one another, this is if you have dependence, right? If they have no dependence on one another, then actually P of A given B, B has nothing to do with A. You all follow me? So if you look at this, I'm going to tell you how they get there. If you look at this, the probability of A does not depend on B. I might as well just put probability of A there. Does that make sense to everybody? So that means probability of A intersecting B is just going to be equal to probability of A times probability of B, or the probability of event A occurring and event B occurring concurrent. It's just the probability of the first times the probability of the second. There's nothing where you don't have to subtract any overlapping area. Do you all follow me, class? He's trying to show you that. And in general, they'll extend this and they'll say the probability of A intersect B intersect C, and you can go on forever. If they're independent, is just P of A times P of B times P of C, and you can extend that forever. Now, when we did that wine business, do you remember how we had the probability of getting 2 of each? Do you all remember that in the wine? So it was the probability of getting 2 Merlots, the times, and this is where this comes from, times the probability of getting 2 Cabs, times the probability of getting 2 Zinfandels, because there was no overlap. One did not depend on the other if you're selecting 2 at a time. Do you all follow me? That's sort of the application to this in a prior problem, if you think about it. I just want to mention this to you. Now, I'm not going to spend a lot of time on this. I'm going to give you some exercises, but the frank truth is this, that if, when you look at this, most of the time it is self-evident. You don't need to do any kind of serious math. Now, there's some other stuff, and this is in chapter 2, because now I'm trying to get into things that are actually, we'll talk about simulation later. He talks about simulating random events and how it's just really the frequency of something happening over divided into the total number of things that can happen, or the outcome. And I think everybody understands what I'm talking about there. So let me get into this. In chapter 2, in your book, I kind of alluded to this last time. Continuous random variables can be any value between a certain range, any possible value. Discrete random variables have only allotted values. For instance, 1, 0, 2, or 0, 1, 2, 3, 4. That would be a discrete random variable. And when we have discrete random variables, he uses something, not a probability density function, he calls it a probability mass function. It's just a statistical interpretation of what's happening. And I'm going to give you some examples so you can appreciate this. It's called a mass, it's a PFM, not a probability density function, not PDF. So let me go ahead and do this, and I'll show you exactly. So problem 211 in the book, it's on page 79 in my book. He has this. Who has a book here? You have a book? So I want to go through this part because I'm trying to get to the important parts of this course, not spend a lot of time on things that are sort of just generally applicable, but not really specifically applicable to engineering problems. So for 211, and you'll see this, because the reason I chose to skip ahead is this will be make a little more sense to you. Go ahead on this one.
Let X be the number of students who show up at the professor's office
All right,
hours.
so students that show up at office. Right? Go ahead.
And the only possible values of X are 0 through 4.
All right, so X is discrete, 0, 1, 2, 3, and 4. There's 5 possible values. Go ahead.
And then the probability of 0 is 0.3.
Now, these are actual probabilities. So the probability of nobody showing up is what?
0.3.
0.3. Probability of one person is?
0.25.
Probability of 2, exactly 2, by the way, not 2 or less.
0.2.
0.2. Probability of exactly 3 equals?
0.15.
0.15, and probability of 4.
That's the first thing I want you to find.
All right, we're going to find this. I want you to just think about this one. I'm saying that we've got a professor in an office. During office hours, apparently he has only 4 students in the class, he can have no students show up in his office hour. That would be 0.3%, or 30%. 25% 1, 20% 2, it means during that hour. 15% 3, and what is 4? What do you know that the total probability of all outcomes is? 1. So what's this one going to be? P of 4 is just equal to 1 minus, this makes perfect sense to you, right? 0.3 plus 0.25 plus 0.2 plus 0.15, correct? And that's what? 0.1, I believe. You agree with that? And everybody follows me. It has to be one of them. So then I think he asks you to sketch this in terms of a probability mass function or something like that.
Just draw a line graph and a probability histogram for the PMF.
Really, it's called the probability mass function or the histogram. It's the likelihood, and this is all it is. Here's, on this, is going to be the possible values for X, or the number of students. So you got 0. Then on this axis is the probability, and it's very simple. This is exactly 0.3. He shows you that. And I'm drawing these it's not really a true impulse. The only thing I'm showing you is its discrete value, and that's it. It only occurs there. Then there's nothing until you get to 1. You can't have 1.2 students. Then this goes up to 0.25. Then you have 2, and it goes up to 0.2. Then you have 3, and it goes up to 0.15, right? Then you have 4, and it goes up to 0.1, I believe. Correct? Everybody? I mean, this is it. I'll show you this. I didn't post the solution, did I? This is what he's going to have. Does it make sense to everybody? It's just a visual interpretation of a statement of the problem. Now he's going to ask some questions about this, but I think you're smart enough. It's going to look boringly simple to you. So now, what does he say? What is the probability of?
That at least 2 students come to office hours.
He's saying now X, the number of students that come to an office hour, is equal to or greater than 2. There's 2 ways to do this. I want you to just think about it, everybody, before I just do it, because it's going to be so obvious. It's almost boringly simple. You'll be bored to tears in a second. 2 or more. Here's 2, right? Or more is this plus this, agreed? So one way to get it is this plus this plus this. These 2 are 0.2, that's 0.2. So it's 0.4 just by going this way. There's 2, 3, 4, right? Correct. Oh, I'm sorry, point. Is that right? Let's see. Yeah, I think that's right. 0.25 and 2 is 0.45. I'm sorry about that. Agreed? What's another way to get that? Think about, if we sum them all, we better get 1, right? So if I have 1 minus this and this, that'll give me the same thing. Do you agree, class? So it's the same thing as 1 minus the probability that the number of students that show up is less than 2. And that's just 1 minus this, which is 0.55, so it is 0.45. Everybody agree with that? All right, what's next?
Probability that more than 2 people come?
All right, now, what's the probability of X being greater than or equal to 2, 2 or more?
It said more than 2. So not 2.
More than 2? Okay, sorry. Greater than 2, what's that? You agree with this, everyone? If you read the problem, think about it, it's that simple. This is just 0.25. Sorry about that. What else?
What is the probability that the professor shows up for his office?
So that's a joke. It says it's a joke. I looked it up. Nobody will show up. And it says professors should always show up. Okay. I don't know how that applies to anything in the problem, but yeah, he's right. Is there another part to that one? Now I'm going to show you a couple other things. Now that is for a a discrete random variable. Y'all follow me in this? This is just what? They call it a probability mass function in his book because it's discrete. Technically, it's just a discrete probability density function, okay? Now I'm going to show you something. Please be attentive here. Now, if you have another problem similar to this, I'm going to put it right here, and we talk about a continuous random variable, I can say this. We're going to have some x is going to be, has certain values, and x is going to be between 0 and, what's the 4? 0 and 4. So that's the, but this is a continuous random variable that's x. It's considered a random variable. Random variable. Random variable means that the outcome is uncertain. It's probabilistic. A non-random variable would be like the output from an amplifier where you had the amplifier gain is 5. If you put 1 in, it'd be 5 out. 2 in, 10 out, so forth. All right, that's something that is not random. It is absolutely, it's given. So when we have this, now these are the possible values. And now I'm going to show you something. This is called the probability density function of x. And it gives you an idea of what this did there in discrete land. And I'm just going to have it this. So here's 0, here's 4. It's going to look like this. And the actual value of this is going to be 1/4. Now, I've got to tell you one thing. You all see the range of this random variable. So this would be 0.25 right here. Is from 0 to 4, exactly, right? Just like this one, when you add up all the values, they have to equal 1. If you integrate the area under this curve, it has to be 1. So one of the first properties of PDFs is if you integrate from minus infinity to infinity, the PDF function, in this case of x dx, it has to be 1. If you look at ours, if you integrate from here to here, or put just the area under the curve, do you all see it's 1, class? All right, so now the next thing I want, what is the probability that the random variable x, that is a continuous random variable, is between 2 and less than 3? It's a little different than the last one. How would you get that? Just think about it. Well, really, the probability of an event occurring is the area under this curve. So if this is 2 and this is 3, it would be the area under this curve. No ratioing here. Do you all follow me on this, class? So what's that going to be? Technically, it'd be the integral from 2 to 3, right, of the density function. I made it constant, 1/4. And then I take dx. So that's just what? Well, from 2 to 3, the difference here is 1, right, divided by 4. It's going to be 1/4 or 25%. Do you all follow me on this? How many have seen this before when we talk about distribution functions? I thought, which class did you say it in?
Statistics. I studied.
Oh, you had statistics. Never. All right, in statistics, they'd show you this. Usually with statistics, they do that. They have discrete random variables. This is a continuous random variable. We're going to talk about that too. I have about 10 minutes. I want to just get this down. Now, there's two other things that happen. Y'all follow me how that is equated to that? There's another thing called the mean of a function, and I'm going to put it over here. I'm trying to just blend all this together so it will make sense. Remember, we got discrete or continuous. No real difference. Now, when we talk about the mean of a function, mean of x, a random variable x, what we mean is this. Go figure. It's the expected value of x, the expected value of x. And it's really given as mean of x. It's just x with a bar over. Now, what is it? It's just this. If it's a continuous random variable, it's the integral from minus infinity to infinity of the function x times the probability density function of x dx. So you take the PDF weighted by x and integrate it. We're going to do this in a second. Y'all follow me? That's the mean value. When you hear what's the average on a test, the mean in a test, that's how they get that if it was continuous. This is the expected value or the mean. When we talk about a mean and we have, this is continuous, a discrete random variable, then what that is a summation. It would be over all values. Let's assume they're positive for now. It would be for I equals, say, 0 to n minus 1, where n would be the number. And it would be of well, let me call it, let me do x. X. Then it would be of x, and it would be times the actual, and I call that, he calls it the probability mass function of x, and you're just summing it. So let me give you an example. I showed you how with the, I didn't do the mean of this one. Let's do the mean here of that, and then do the mean of the continuous one. I'm not spending a whole lot of time on this because I think you guys will see this fairly easily. Let's go ahead and get the expected value of this random variable. Well, it would be what? It's going to be an integral over here, correct? It would be an integral from 0 to 4 of the value x. That's the thing we want the mean of, because that's the random variable, times the probability density function. Well, the probability density function is just 1/4, and it's dx. Do you all follow me on this? Everybody? Or what's that going to be? Well, That's 1/4. The integral of x is going to be x squared over 2. And then we have to evaluate it from 0 to 4. That's going to be what? 1/8, right? And then it's going to be 4 squared is 16, or this would be 2. Take a look at this and just see it for a second. Y'all agree with that? Do y'all see this? I know it's getting late and this is boringly simple, but trust me, there's some subtleties that you're going to see. I've only done it for positive values. If there were negative values, say the probability density function started here at -2 and went to 2, what would the mean be, do you think? If it was constant from -2 to 2, what?
0.
Right? It would be 0. And that just something to keep in mind. I don't want to spend too much time on some of the things you have to consider, but that is the expected value for that. What's the expected value for this based on what I just told you there? Let's do it over here. All right, this is the density function, just like this was the density function there, okay? So let's go ahead and do it, and we're going to do it from here. So the expected value of this discrete process, right, would be what? Probability of 0 times 0.3. Agreed, everyone? Times the probability of 1 times 1, it's just 0.25. Plus what? Probability of 2 times 2, or 0.2. Probability, get rid of that. Probability of 3 times, 3 times the probability of 3, which is 0.15, plus the probability of 4, right, times 4. Agreed, class? What is that value going to be? What is it?
Sorry.
This one you don't worry about, right? So I got what? 0.25 plus 0.4, right? Plus 0.45 plus 0.4. Do you agree with that? And what's that value? Is that right? 1.3. What'd you get?
1.5.
Let's see. Hold on. This is 0.4 here. So let's see. 0.4 and 0.4 is 0.8.
1.25.
Yeah. What did you get?
It's 1.5. If you add all this up, it's 1.5.
Yeah. All right. So that's what it would be for this one. Now, the probability of all these events occurring for this one is different. I had a constant probability density function when I did that other one, okay? But that would be the mean value. Now, another thing I'm going to just do, I was going to get to the PowerPoint, so I'm going to show you this. This is it's called the first moment. How many have had statics and dynamics and all that stuff? One person, that's it? Remember in statics and dynamics, you did moments? You took like moments of equations. For instance, when you calculated the shearing stress, it was the force integrated over the distance on a cantilever beam would be equal to the shearing stress. These are called moments. They're weighting a density function by a value of the function that the statistics are involved with. This, what I just did you with the expected value, that's called the first moment. Now the second moment of this stuff, which this gets interesting. And then we're going to get something called the standard deviation. You've all heard of that, right? Standard deviation and variance. Okay, so the second moment, or the expected value of x squared, let me do it for continuous time, but it follows in discrete time as well. The expected value of x squared is the integral of x squared from -infinity to infinity times the probability density function of x dx. This makes perfect sense. Before it was just x to the first power. Now it's x to the second power. This is called the second moment. You all with me? So for this one, it's straightforward. It's just an x squared times the PDF. And if it was discrete, what do you think would happen if it's discrete? It would just be a what? It's going to be a sum of what? Then it would be x squared, right? Times the probability mass function of x. It's just the statistical chance that it has the different values. Do you agree with that? And then here, x would take on all values. I'm going to go from 0 to n minus 1. That's all it's going to be here. With me? All right. What would it be here for that one I had before, where the PDF was 1/4 from 0 to 4? Remember, I had the PDF was just equal to a constant of 1/4. What's the expected value going to be of that? And this is true from 0 greater than x less than or equal to 4. Well, it's the integral from 0 to 4, right, of x squared times the PDF, which is 1/4, times dx. Can everybody follow me on this? Try to make it as simple as possible. It really is this simple. When you look at it, what do you get? I have a constant probability density function. Usually the PDFs are not constant, so the integrations get a little tricky. But in essence, this is it. So what's that going to be? Well, the 1/4 comes out in front, right? I integrate x squared, I get x cubed over 3, evaluated from 0 to 4. And that means, what do I get? I get 1 over 12 times, and really, I might as well just put 4 times 3. And times, and it's going to be 4 cubed, right? Well, that's really 4 squared, or 16/3. That would be, and this would be expected value squared right here, of the second moment. Correct, class? Now, there's something called the variance, and I'll just tell you what this is. We talk about the variance, variance. That's really the expected value of quantity x minus x bar, the mean value squared. Y'all with me? I'm just showing you this now because I want to, and I'll do it with the continuous random variable. I think I got 1 or 2 minutes left. Now follow me on this. Here, anytime you see expected value of anything in here, you take that anything and you multiply it by the PDF function and then integrate it over all possible values. Y'all with me? That's all it is. So for this one, it's going to be the integral from minus infinity to infinity of this x minus x bar squared, and then it's going to be times the PDF of x dx. Now I'm going to show you something here. I'm going to go ahead and do the squaring operation. You're going to see something. So when I get this, by the way, this symbol for variance is usually sigma x squared. Have you all seen that? Sigma as a standard deviation, sigma squared would be the variance. How many have seen that before? It's done all the time in statistical stuff. If you do anything out there, if you're a shooter and you talk about the, average shot size and then, or the average velocity of bullets leaving, and then there's an average value, just to sum them all up divided by the number, then there's going to be something called the standard deviation. That's how they get this in discrete, but I'll get to that in a second. I'm talking a little fast because I'm almost out of time. So for this, take a look at what it is. When I square this thing, I get the integral from minus infinity to infinity of x squared times the PDF of x dx. This is just the first term of the squaring operation. Then I get minus, and it's going to be 2 times the average value of x, right? Then it's going to be times the integral from minus infinity to infinity of, and it's going to be x in here. Because when you multiply these two, like when you go ahead and square this out, you get x squared minus 2x bar x, and then it's going to be plus x bar squared. You all with me, class? So then it's this times the PDF, you'll see why I'm doing it, of x dx, and then finally it's going to be plus x bar squared, that's a constant, times the integral from minus infinity to infinity of the PDF of x. And I'm going to stop there. You all follow me? So this is the same thing as the expected value of x minus x bar squared. It's called the variance. Let me just complete my thought here. The standard deviation is sigma x, and it's just the square root of sigma x squared, this. So take a look at this. Let me finish my thought here. Just be attentive here. What do you know the integral of a PDF is from minus infinity to infinity? Anyone? 1, right? It has to occur, right? If you just take the integral of the PDF alone, from 0 to infinity, in other words, where it can occur, it's got to be 1. It's got to be somewhere in there, right? So if that's 1, this is just the mean squared here. You all see that? What's this? X times the PDF integrated over all possible values is the mean. Isn't it X bar? Can you all see that? This right here is just X bar. You all with me? This is what? The second moment. We did that earlier, right? So when we talk about the standard deviation, and I'll leave it at this, it's really the expected value of x squared minus, and take a look at this. I got minus 2x squared plus x squared. Y'all with me? So, or minus x squared, x bar squared. Take a look at that. Minus x bar squared. Here's minus 2x times x bar times x bar, right? Plus x bar squared is really minus x bar squared. And this is, and it always will be, that is the variance of a function. So if you got the second, if you have the variance and you have the second, or have the mean, you can get the second moment and vice versa. If you need the variance and you have the second, or you have the second moment and the average value, you can get that. You all with me, class? I needed to throw that out there. Can you all see how you do it for continuous time? Instead of having integrations, you have summations, right? In the summations, you wouldn't have a probability density function, you'd have a probability mass function, then you would have a summation where that value of x would be it would be discrete values. Okay, sorry I held you so long. Does that make sense to you? I'm trying to get us into parts of the course that are directly applicable to a lot of electrical and computer engineering stuff. Thank you for bearing with me. I don't know why I'm so tired.